Hey, so this is another solving beam reactions problem. So what we're going to do is we're going to solve the support reactions at A and B due to the applied distributed loads. This is, the approach that we're going to find or use. We're going to draw a free body diagram. We're going to break the distributed loads into triangles and rectangles because we know what to do with triangles and rectangles. So if you don't know, check out the previous video. And then we're going to solve the resultant forces and find locations of those distributed forces. And then we're going to apply the equations of equilibrium. So hopefully this makes sense. This is one problem that I tend to give every year in some shape, fashion, or another. And part of the reason is because when I was working as a civil engineer, one of the first things that my boss gave to me was a job where we had an addition going lower than an adjacent building. So, I just did a quick Google search because what do you guys do? You do Google searches, right? So I just did a quick Google search here and I looked and I said, okay, well, what does that look like? If I do a low roof, drifted snow, this is what came up. This is one of the pictures, and I love this picture because what it illustrates is this. If we look and we say, well, we have a beam right here, what do you notice about the snow? The snow drift makes a load sort of along those lines. So if you picture this, that it's going to be heavier on one side, and as we get down, it's going to level off at some point. So there might be a uniform condition down here. And then we're going to end up with some, drifted triangular portion up here. So this is real world. This is, the real deal. And what we're going to do is we're going to go ahead and we're going to solve this problem. Okay. So I'll show you how. We're going to walk through it. But first, let's go and draw that free body diagram. And when I draw the free body diagram, I like to throw in my unknown reaction forces and label them. Okay, I also like to show this distributed load. And in this case, I look for areas that I can break it up into known, like here's a rectangle, for example, and here's a triangle. So I don't know if you can see it. So when I draw my uniform load down here on my free body diagram, I'm actually going to break it up like that. So let me show it like that. Okay, and now we need to figure out, well, what is the magnitude of these distributed loads. So we know we have our 500 pounds per foot. So I'm just going to take that and bring it back down. So I know I have 500 pounds per foot here. Okay, and then how much is left over? In other words, if we were thinking about snow, we have our base snow load down here, right? How much snow is left over? Well, if we take our 1,000 in this case, how much did we subtract off in the rectangle? Well, we subtracted off 500. So what's left here is, this height goes from essentially at this point 0 pounds per foot all the way up to, I'm gonna, don't write 1,000, 500 pounds per foot. Why is it 500? Well, we add 500 and 500 in this total height here. This total height here is going to be 1,000. Okay, so that's not what we're looking for, but right now what we do want is we want this triangular load of 500 pounds per foot on top of a rectangular load of 500 pounds per foot. So all in all, at this end, if we were to write this in or say this total load is going to be 1,000 pounds per foot, okay, PLF. So pounds per linear foot, that's what we know and when we add these together. Okay, I also like to throw in here, if I know my dimensions, I like to put my given dimensions in, right? So we have 6 feet, 4 feet. I like to show my coordinate system, and we're pretty good. The other thing that I always add if I have a distributed force is I look for, well, where's the centroid of that force? So here, for example, we could look and we can say the centroid of the rectangular load is going to be in the middle of this beam. So I just like to, use a different color or use a dashed line or something to represent the centroid of that rectangular load. Similarly, what I like to do here is take this and represent the centroid of that triangular load. So in this case, we have a centroid of a rectangular load, a centroid of a triangular load, and I'll just solve those over here. So if I come over and I'd solve for, the centroid of my, I should say the resultant from the triangular load. If you remember, this is going to be essentially the area this triangle gives me the total weight of that load, or snow if you want to call it that. So what we have here is a half times 500 pounds per foot times 6 feet. And when we do that out, 6 times 500 is 3,000 divided by 2, it will be 1,500 pounds. similarly, what we know is we have the rectangular load. So RR is going to equal, in essence, it's just the area of this triangle. So 500 pounds per foot times the total length, because the 500 goes to the total length of the beam. So this is going to be 500 pounds per foot times 10 feet. So that's just 5,000 pounds. Okay, the other thing I like to do here is I like to know, well, where is that in relationship to where I'm going to sum my moments? So in this case, I know I'm going to sum my moments about point A, so I know I have one distance to my triangular load. I also have a distance over here to my rectangular load. And what are those distances? Okay, so in this case, we're closer to the big end of the triangle. And if you remember, if we have triangularly distributed loads over here, what we're going to say is, what does this look like? If this is our triangle, our centroid might be right here, and what we're going to say is, if this is length L, okay, the distance from the big end is going to be 1/3 L. So in this case, what are we going to say? Well, this distance here is going to be, well, we have 6 feet divided by 3 is going to be 2 feet. Okay, and then to our rectangular, well, the rectangular, if you remember, a rectangular, if we have a distance of L, what is that? Well, our rectangular resultant is a distance of L over 2, right? So this is L over 2. So when we come back to the resultant here, what do we do? Well, we take 6 plus 4 is 10 over 2. That's going to get us to the middle of the beam at 5. So once we have that, label by, but once we have that, now we can go and apply our equations of equilibrium. So this is the fun part. This is when we get answers, and this is where we go. So let's start with the easy one. Sum of the forces in the x direction equals 0, and the only force we have in the x direction is AX. So AX equals 0. All right, that's, again, it's the easy one. It's the one I love to do first, but get the easy ones out of the way. Okay, so we have the easy ones. Don't forget them, because if you forget them, your answer is not complete. Let's do some of the moments next. So when we sum moments, again, we look for any moments or any forces that don't act through point A. Because if you remember, a moment is a force times a distance. And what we're going to do here is we're going to say, well, we have RT times 2 feet. That's the moment arm, the distance between the line of action of RT and point A, vertical force, horizontal moment arm. Okay, and then what we have here is the rectangular resultant as well. So rectangular resultant times 5 feet, and then we have BY times 10 feet. All this needs to equal 0. And you notice I left out signs here. So RT is causing rotation, this direction. RR is causing rotation this direction. They're both opposite of our positive sign convention. Okay, so those are both going to be negative moments. Okay, so we'll write that in as negative. And BY, again, we can do this with BY, but BY is going to be causing rotation. If you hold your pen at point A and rotate this thing, it's going to be causing rotation in a counterclockwise fashion, and that is going to be consistent with our sign convention, so that's a positive. So this is good. So now we just need to substitute in minus 1,500 times 2 feet. I need my pounds in there. Minus, what do we have? 5,000 pounds times 5 feet plus BY times 10. This is nice. I always love an equation that only has one unknown. So when we have one unknown, we can go ahead and solve it. 1,500 times 2 is minus 3,000 pounds minus 25,000 pounds. And plus BY times 10 feet equals 0. So at the end of the day, what are we going to do? We're going to get BY equals, well, we add the 3,000, add the 25,000 to the other side, divide by 10, and 3 and 25 gives me, what, 28,000 divided by 10, so this is 2,800 pounds. It's nice, we can circle it, we're good, and we've solved it. Okay, and then we can apply our last equation of equilibrium. So here we have some of the forces in the y direction equals 0. The forces up are going to be positive, and what do we have? We have AY, minus RT minus RR plus BY equals 0. So this is cool. We got AY, we don't know AY yet. That's what we're going to solve for, minus RT, which was 1,500 pounds, plus RR, which is 5, let me write that over, which is 5,000 pounds. plus by, and in this case we know by is 2800, so let's substitute that in. It has to equal 0. And I made one mistake. Do you see it? I copied, I put a plus here instead of a minus. So a good thing about erasers is we can come in and fix the mistake. So maybe you picked that up already. But here we go. Minus 15 minus 5 plus 28 equals 0. So what do? We add the 1500, we add the 5000 to the other side, we subtract 2800, and at the end of the day we get AY equals 3,700 pounds. Okay, so we can circle that, we can be good. But again, with this one, the big thing with the approach that you have to do is you have to, the way that I like to do this at least, is to split this load up into shapes that we're familiar with. So we're familiar with, these rectangular and triangular shapes. So why not take the complicated trapezoid, break it into known shapes? It makes it easier, hopefully makes your life easier, hopefully helps you solve that homework problem that you're working on late at night, and helps you in it all. So that's what this channel is for, is to try and help you. So till next time, keep working hard, keep looking onward and upward.